let's talk about the material that you will have viewed on the video. So what was the subject of the video? Anyone? In rough terms, Pius.
So the differences between stocks and agent-based models in regard to like modifying it and putting in more stochastic, not stochastics, but like extra parameters.
Yeah. Good. Yeah. What went by the somewhat unwieldy name heterogeneity. Basically, it's about differences in the population that you want to keep track of. I'm found to lapse from the quinting. Right? You want to keep track of differences in the population, and that's different, as Pius suggested there, between the two major traditions we've been examining. On the one hand, the predominantly aggregate tradition of using stocks and flows to summarize like the state of a situation, the state of a population, particularly on the one hand. And on the other, the individual-based tradition involving agent-based model, where we have individual agents for representing individuals, right? So I'd like to talk about this a bit and make sure that some high-level points really sunk in with respect to this, okay? Okay, sorry. So somehow this didn't come up. There we go. Okay. So we've, just to make sure we're on the same track, we've gone and looked at high-level aggregate models, right? This is our archetypical or paradigmatic sort of model of contagion, susceptibles, infected, recovered. And at any one time in this model, if you were to run this model in pre-time, the current state of the model will be characterized by a certain number of people susceptible, a certain number infected, and a certain number recovered, right? On the same page for this. By contrast with an agent-based model, where we might have, people in the context of a community with homes and workplaces and community places. You may remember this, and each person has some daily circulation among different locations, differing by their age in years, which is a continuous quantity, and they have some sort of infection state alongside that. This is an individual-based characterization, right? I'm characterizing the rules for agenthood here, but at the end of the day, when we simulate this model, there's many agents who at any one time are in a certain state with respect to the left and a certain with respect to the right. I see a hand up, and neurons fade, but this may be an error. Okay, speak on, young Eric.
So my thought while I was watching this video was, isn't this just basically covering the principles of object-oriented programming in just a visual scenario, like any logic making it a visual programming instead of programming?
You could say it's certainly leveraging object-oriented programming for agent-based modeling.
For agent-based.
Agent-based modeling has a close traditional affiliation with agent-based modeling because traditionally it was recognized that we can treat objects in an object-oriented programming. We have individual objects. There might be instances of a class, right? They're actually, I'll use the term reified, like there's a thing there we can point to. They're actually individual bits of memory allocated, right? And it within an agent-based context, those correspond to individual agents, right? And it's no surprise in that regard that most, although not all, agent-based platforms are object-oriented in their creation. They use object-oriented programming languages, whether it be Java or C++, or indeed variants like Objective-C or what have you. You can readily implement agent-based modeling tools within those. Now, stock and flow models, by contrast, hew to a rather different paradigm, right? Where we have instead something more directly similar to what we see with the ordinary differential equation. We have state variables that count, right? The number. But the lecture was specifically in the video. So that's a good observation, Eric. I appreciate that. It's somewhat orthogonal to, somewhat, perpendicular to the goal of the model, although a worthy observation. The goal of the video, which was to emphasize how do we handle characterizing differences in the population, characterizing heterogeneity. So suppose we have a population like this, and we wish to keep track, for example, of people in the population here by province territory in an aggregate model. What would we do in this model that lies before? So what would we need to do if we want to keep track of spread of infection in different provinces, where we assume for simplicity that they're not mixing? We assume that they're separate. What would we do? So I'm delighted to see Eric has his hand up. I'm going to go with Liam for some to get others. Yes, Liam?
You would make a copy of the model for each province or territory.
You got it. There's basically going to be layers of the model, right? One for each province, right? Now you'll note that this is a global change. What I mean is it's affecting basically, across all these stocks. There needs to be not just a susceptible Saskatchewan, a susceptible stock for Alberta, a susceptible stock for BC, a susceptible stock for Manitoba, and so on. But there needs to be also those for infective and recovery. But more than that, there need to be flows for every one of those, right? So there's a new infections in Saskatchewan flow. There's a new infections in Alberta flow. There's a new infections in BC flow, et cetera, right? So we have these layers. And that's not worrying about mixing between them, which we'll get to. Right? So let me contrast that with, or I'd ask you to contrast that to what goes on in an agent-based context. So what do we do here? Yes, Eric. Yeah.
You would just add another parameter.
Yeah.
In the code, you would separate them.
That's right. That's right. That's right. Or if I'm to take a nod again to your comment on object-oriented program, it's like adding a field, right? And an object-oriented program to each object, right? So we tag each person by what province territory they're in. We add a wee bit of data to them, right? Now, it is notable that if we do this for, I think I stand remiss. I have shockingly failed to share my screen. Well, better late than never. And I would certainly say better late than never. I go by eight. Anyway, so here, what we'd be doing is adding a parameter, right? That would distinguish what province or territory did. Now, in terms of the amount of resources used, how much would it increase the size of this model in terms of its runtime footprint, the amount of memory used by it, if we added that bit of information? Okay, I see a Jihan whose hand is up too. Yes, yes. Okay, so each agent will be carrying some amount of information. Maybe we need, once we consider provinces and territories, there's 10 possibilities. Maybe we use 4 bits, right? And so we'll keep track of 4 extra bits per person in the model. And maybe to already keep track of the information that's here already, maybe that increases it by, depends how much it would use, maybe it's by 10% or something. By contrast, in a stock flow model, in a stock flow model, we need to get this clear out of the way. In a stock flow model, not this one. I didn't want Harrison and links by territory, although that would be a worthy endeavor. Okay, no. Oh, come on. Did I close it? Okay, well, I will summon it. If we wanted to do it now, how much would that increase the size of this model footprint in memory? So are you going to help me with Shiva?
Yeah.
Yes.
Right.
Yeah. So if it were, for example, only Alberta versus Saskatchewan, we would double it. In this case, it's a layer for each province or territory, and so you're going to multiply by the number of provinces and territories. Yes, Eric.
Isn't that really for this sort of model?
Yeah.
You don't really have to worry about the memory footprint.
Okay.
It's so insignificant.
Okay, we're getting to this. We're getting to this.
Increasing by double is basically no.
Okay, so that's a good observation. If you increase this by a factor of 10, it's still going to be markedly smaller amount of memory that's needed than for anything else, right? Where you might use that amount of memory if you had only 10 agents, for example, right? And you might need 100,000 agents or something. And so you might say, reasonably so, that it's kind of small potatoes. But I want you to start thinking a little bit more broadly about this too. So suppose we wanted to go beyond province territory and we wanted to have 8 as well. Okay. Suppose I want to keep track of people's age as being one of 17 age groups, 0 to 4, 5 to 9, 10 to 14, 15 to 19, all the way up to 85. Maybe 80. In any case, 17 age groups. And suppose we wanted 10 divisions for the province territory. How many combinations now would we have? How many different? Well, for the ABM, what would we need to do? What would we need to do if we want to keep track of age as a fixed quantity? We're not going to simulate them aging. A later discussion next time. But instead, it's a fixed thing that it's one of these 17 values. What would we need to do? Yes, Alex.
Just add an extra parameter.
Extra parameter, right? Keep track of one of those 17. So we might add one byte of information for each person that keeps track of which age group they're in from 0 to 16. Okay. Good. What would we need to do for our model? Oh, come on. It's this one. Yes. This one here. What do we need to do? Jihan? For each of the previous terms. So what I want to emphasize here, and this is towards Eric's point. The initial base level of computation here for this sort of model requires markedly less, dramatically less amount of memory and amount of computational horsepower to simulate at a base level this versus a simple ABM. There's a lot more moving parts with the ABM, a lot more going on, a lot of agents and things like that. But I do want to emphasize when it comes to heterogeneity, this point that what was said here for the stock flow, the aggregate model. What Jihan pointed out is that as we add new types of heterogeneity, it's multiplicative. It grows, I'm going to say geometrically, meaning 10 for the first times 17 for the second. If you wanted to keep track of not just their current province territory, but the province territory in which they were born, that would be another times 10. And that starts to grow multiplicatively in a large way. I will tell you, we readily build models which have for each stock 168 compartments for different subsets. I've seen some that might have 500 or 1,000. Now, it's still comparatively small total amounts of memory. But Eric, were you gonna say something, and I'll get to Agina here?
No. With a lot of parameters, if you need to isolate them, you can, but you could also build a lot of the parameters into the map itself, where you don't need to multiply it.
Okay, well, so that's an interesting thought. We'll come back to that in a little bit. Let's pursue that in a few minutes because there's some subtleties there, but it's a really good thought, and I really appreciate you putting it forward. And you're indeed correct that there are finessing ways to sort of fold it in a way that you might get a lot of the effects you're hoping to get without blowing up the model, so to speak. But Agina.
This wasn't really a question, but I just remember even in the first lecture, you said something specific words that stuck with me were combinatorial explosion.
You get a combinatorial explosion.
Yeah.
Yeah. And I'm gonna come back to this because with a nod towards Eric's point on the total amount of memory, I mean, you might say, well, look, even if I increase the size of this model due to heterogeneity by 1,000 times, it's still comparatively low amounts of work to simulating. Low amounts of work to represent it, like in memory, the amount of storage you need in memory to simulate it is comparatively small compared to a medium-sized ABM, ABM with a medium-sized population. And that is true. That is true. But there are other facts that we'll come back to in a moment. Besides memory footprint in raw computation. Here, what I wanted to emphasize, and I don't want to get lost, it'll be in your interest to not have it be lost, is that in this sort of model, as you add in dimensions of heterogeneity, I'm saying like 8, and then you add in province territory in which they currently live, and province territory in which they were born, and their current immigration status, or what have you. You add in their income level by decile, like 10 different income levels. So you add in their education level or what have you. Whether they're a smoker or not, current smoking status or status with respect to diabetes or with respect to flu or what have you. You're adding multiplicatively the number of different divisions that are needed. In an ABM, so that's for the aggregate, in an ABM or an individual based characterization, you're additive. So each small component here, like you want to add age groups, you add a parameter for each. if you want to keep track of province territory in which they're current resident, you could add a parameter for their current residency, by province territory. You could add for birth territory. The point is it's additive, not multiplicative. It's additive. You're adding little bits of information. You're tagging them, each person with a bit of information, but it is needed for each person in that population, right? And this is an important point that we're gonna come back to, but I just want you to be really clear. Adding heterogeneity in for an aggregate model is multiplicative. Adding it in for an individual based model is additive. And as you go and you add more and more types of heterogeneity, more and more types of differences, multiplicative things tend to add up. It grows, as we say, geometrically, or the continuous version of that is exponentially. And easily, each time it will at least double, right? If there's only two possibilities you want to keep track of, right? Whether someone's a working age or not, or something like that, it will double the size if you go have that end of the footprint of the model, or the running time of the model. Whereas, adding a bit for each person is going to be a much smaller increment to the amount of memory needed in terms of an extra proportion, how much that grows proportion. Now, I want to come back to some points, but first, I do want to ask, how much of the model does the change affect? So, suppose I were to say, okay, with this APM, I'd like you to add in a component so it's a parameter that is going to specify their marital status as one of four. Marital status is one of four values. So how much of the model does adding that affect? If I go add that in, how much does it require me to change the model? Very, very surgical. It's very small footprint in the model, right? It's a very localized effect. If I want to, by contrast, add that in to my SIR model, how much of the model do I have to modify?
Depends on how many you've multiplied it already.
Well, okay, but okay, so that's a good point. At the least, it requires changes across the model, right? To each of these logical components. Now, within these packages for modeling, any logic included, but broadly supported for many packages, you actually use a mechanism commonly called subscripting, or more informally arraying. But the idea is that you simply say you give a subscript to susceptibles. You subscript it by age. So you have susceptible sub 0 for age category 0 to 4. You have subscripts of 1 for age category 5 to 9. Subscripts of 2 for 10 to 14-year-olds, etc. So you subscript it. But the point is, you need to change things across your model. So the bigger issue here is often not how fast will the model run or what its memory footprint is, because Eric's exactly right. That the amount of memory and amount of storage, but also the amount of runtime required for an aggregate model is often so small, like orders of magnitude smaller than for an ABM, an individual based model, that even if you put lots of subscripts in, that's not going to be deeply debilitating. what we'll start to, with you in just a second. Okay. Nicola.
I'm just wondering,
Yeah.
that also means then, so while at least the memory footprint is very small, what it really is like more curriculum that complexity.
That's correct. That is correct. And there's two aspects of it. One is the detail complexity of just having to go and modify all these things across the model. It's just a lot of complications, a lot of bookkeeping that has to be done. Oh, I need to update that and update that. And it's kind of promiscuous. It requires these changes across the model. But the other thing is, it actually starts to obscure the model logic at some point. Because the model starts, like, I mentioned subscripting. If you don't subscript and you have to copy this, I think Eric was referring to it, their life's madness, right? You're going to be having like a zillion copies of this. You've got to, I'm exaggerating, right? But not by a lot. There's a lot of copies, and you've got to do bookkeeping visually, like where they are, and go modify them and copy them again. That way would be, just beyond the pay. But even if you have subscripting, the subscripts start to dominate the logic of the model. And you end up being so distracted by all these subscripts, you kind of can't see the forest for the trees. You can't see the logic. The core logic of the model is lost in this welter of sort of detail about like which age group, which province you're dealing with, et cetera. And the equations or the formulas that you have get dominated by this sort of bookkeeping that's involving these different sort of subscripts that you're dealing with. So Nicola, you put your finger on a key thing, yes.
And so this kind of going back to Eric's point with object-oriented programming, this kind of thing violates the principle of trying to make sure that you have things like drop, essentially violates drive.
That's right.
All this bookkeeping, you change one thing, you have to change another.
Exactly. You have this coupling across the model that one conceptually small change leads to like this explosion of sort of bookkeeping needs to modify, right? There's not this separation of concerns, this neat division into, I change this in a small localized way here, change that. But with ABM, there is more of this division. There's a more sort of surgical, artful, small changes that are required. And these in practice tend to be really important because that's where, when you have to do the bookkeeping yourself, when you have to modify things at many levels, that's where errors creep in. That's where oversights occur. That's where the model can become inscrutable, like not transparent anymore, where it becomes cumbersome and just awkward to adapt or awkward to respond to new learning, right? Maybe the learning suggests, oh, I'd like to examine this effect of income, but adding it in is so burdensome, so as I say, promiscuous. It just requires such massive amounts of bookkeeping. It starts to bog down the learning and bog down the opportunity to learn from the model and to experiment nimbly. And this is something you're absolutely right. And you and Eric are to be, really heralded for putting your finger on this, because in software, we try to build the right abstraction. We try to build the abstractions that buffer us from change. We try to build in a way that will be nimble to the changes that are expected to occur from a client or from across the lifetime of a project. We try to build the abstractions that will be conserved and will be general enough to handle changes without requiring the madness of having to change everything. And within system dynamics aggregate model, within stock and flow aggregate modeling, this is one of its core vulnerabilities is that, you know, it can explode, but it's really the detail, what might be called detail complexity, distinguish it from dynamic complexity. It's not about emergence, it's just the bookkeeping needs as you add in more types of differences. Yes, so Eric.
How about a hybrid approach where you have agents that represent a group of things and maybe you have a,
Yes, yeah, good man.
could not take the advantage of both?
Yes, there's potential for having, for example, agents who, for example, you could have different class of agents that would keep track of different common groups or what have you as an agent type and hide the details of needing to maintain information across all agents in the population. You could also have some of the model that's more detail oriented where you need to keep track of detail captured at an individual level. And we'll come back to this with hybrid modeling, but kudos again to Eric for putting his handle on it. For example, it may be that once people are infected and those who reach a certain level of severity, we want to keep track of their hospitalization status. We want to keep track of what medications they're on. We want to keep track of, you know, where in the healthcare system they're currently located. And it would be an anti-pattern to try to say, well, okay, we're going to record that for everyone in the model. Instead, we could eventually turn people at that level actually into agents. And then say, essentially, there's a pool of these agents, and we'll keep track of their heterogeneity in an agent-based way. But for the broader population, where we don't have to keep track of many types, we'll keep track of that in an aggregate way. We won't need to make distinctions between people beyond a few base categories. And that's a really important insight. And it gets to, you know, a lot of the motivations for combining these methods. But I want to come back to another issue. So suppose that we wanted to keep track within the population of people's geographic location, where they live in Canada, as a continuous quantity, as a sort of latitude, longitude, or equally, if we want to keep track of their income or even their age as a continuous variable. So I'll start with an age-based model. How do we do that? And suppose we want to keep track of like their age in years as a continuous quantity. What would we need to do? Yeah, we'd add a floating point variable, for example. Good. So here is in fact age in years. Well, it's a double precision floating point. Yeah. So we have this here. Okay, now we go to do that within our stock flow model. And we want to keep track of people by their age and years on a continuous basis. Can we do that? Continuously.
Possibly using statistical analysis stuff, but that's very complicated, I think.
And will involve imposing a lot of assumptions, which will be pretty tenuous. Yeah. So the issue here is we know how to have layers here by age group, right? So we can have a layer for age group 0 to 4, age group 5 to 9, age group 10 to 14, age group 15 to 19, etc. Up to 85 plus, what have you. Or we can even do it by age 0, by integer ages, like age 0, age 1, age 2, age 3, right? You have different layers simulating it. even putting aside aging, putting aside the need for aging, we're going to talk about that next time, but putting that aside, we could have a lot of layers, but it still wouldn't be continuous, right? We wouldn't be able to capture continuous variables. What we have to do is have, I'm going to use this term, this is important, discrete approximations to continuous values. We have what's conceptually a continuum. Of age, and we have to kind of chunk it up into age groups, for example, right? Just to make us very clear about this point, in an individual-based model, in an agent-based model, can we keep track of continuous quantity? Yes, we can. Just the data to be stored by the agent, right?
That's kind of the foundation of it, like susceptible to this quantity.
Well, okay,
Not per agent.
it's not per agent. Like susceptible here is a continuous quantity. You're absolutely right, but conceptually it's a count of susceptible, right? It expresses a quantity involving the number of susceptibles. It's not on a per agent basis, just like you said. But in an agent-based characterization, can we keep track of continuous? Yes. So there is one quantity that is continuous here in thought flow modeling, which is time, and time is modeled on a continuous basis, as it can be in agent-based modeling. We can have continuous time. Events can fire as quickly or as rarely as they need to. There's a lot of agent-based modeling that's done in discrete time steps only, but there's no inherent reason for that. It's a bit easier to implement. You don't need an event schedule. Here, by contrast, you cannot have continuous quantity stored. To do that, you need something called a partial differential equation, which allows you to basically express not just time as a continuous thing, but say age or income level or geography, geographic location. So if we wanted to keep track of geographic locations for an agent-based model, to someone's latitude, longitude, what would we need to do? Just to sort of drive this point home, what would we, okay, now I did the reverse. Okay. If we wanted to keep track of geographic location here, latitude, longitude, as each of them expressed as a double precision value, what would we need to do here? Yes, fine.
Continuous variable.
Yeah, continuous variable. Yeah. Yep. Keep track. And there's good reason not to just treat it as doubles. There's actually good reason to treat it as a geographic location mathematically, because there are certain quantities which don't make sense actually for latitude, longitude that you assign to a double that wouldn't make sense. And there are certain features geographically about like the North Pole and the South Pole being certain special points and so on that are not, you're going to lose that information if you just treat it as doubles. So what I'm saying is you probably actually have a data type that's that expresses a certain type of coordinate. But the point is, it's just a piece of information at the level of agent. Yes.
So then anyone already stored.
It does. It does.
Agent. Because you have functions like get X and get Y.
Yeah, that is correct. You have get X and get Y, but you also have the ability, as some people here know, to assign geographic to place agents in a geographic environment and to give them geographical locations and to have them move around the geography and have query the geography and go to the nearest hospital or whatever. Okay, so to be clear, geographically capturing geographic information here has a wee bit of subtlety with it, but it's readily doable. We can capture that information readily. If we want to capture geography here, if we want kind of to capture different infection and different over the geographic landscape. I'm deliberately sort of waving my hands back. What do we need to do here? What's an easy thing, or what's one way to try to deal with that? Remember, when you have a continuous quantity, the answer is to you want to keep track of conceptually continuous quantity, discretize it, you chunk it up into possibilities. So what you would put into place is patches, right? Patches of areas where there's a certain number of susceptibles. After all, the quantity of susceptibles, like having a number of susceptibles, almost implies it's over some non-zero area, right? Otherwise, it'd be density. We won't talk about. But you might have different geographical areas, each kilometer by kilometer, some number of susceptibles in that area. And then you'd have another one. So you could subscript this by patch, right? A patch within of geography. But it wouldn't be continuous. It would be a discrete approximation to an underlying continuous space, right? For the case of an aggregate stop flow. And that too can rankle. That too can be awkward to change sometime. If you want to change your resolution as a result of learning, as Nicola was indicating earlier, you want to change the resolution with which you approximated things. It might involve a lot of headache going and changing it throughout the model of what resolution is trying. Now, Eric was commenting earlier, you might be able to, like in some cases, you might say, well, look, wait a minute. Rather than subscripting into 10 different income categories, maybe we want to somehow describe in some sort of way how income affects the likelihood of being like the context to represent the fact that people at lower income levels may have more crowding in their living conditions, or they're involved in more essential work jobs, which expose them to more infection and population or what have you. The thing is that like you would have to start to wonder, okay, so how am I going to characterize income? So maybe I'll talk about the mean income in the population or the median income in the population and have a formula that expresses
Or have a mean distribution.
or you have a distribution, but here's the thing, you're going to want, if you have a distribution of income, so you say, okay, there are some people who are lower income, some high, you're going to want to keep track of, for people of like lower income, you might be interested in how many of them have gotten infected, right? And to keep track of that, or how many times they've gotten infected, they'll come to in a minute. But unless you break that out as a different stock or something, you keep track of that number, you're not going to be able to capture that. You might be able to say something about, well, okay, we will try to take income into account by saying if the income level in the population, it's, if it's concentrated in the lower side, people are more likely to get infected, but it's still for the population as a whole, unless you're breaking things out into pieces, by pieces, I mean, stratifying at some level, like keeping track of different numbers. But you might keep track of like a low income person versus a high income person, susceptible, low income versus high. In fact, I do want to pose though that question that I alluded to. And this will get us thinking some about proceeds we'll talk about more next time. So here we have a little population that involves susceptible, infected, recovered. Remember this, people circulating in the community, right? So if I wanted to, within this sort of individual based model, keep track of how many times a person had been infected, could I do that? Could I do that? How would I, could you give me a way in which I might do that? Like just at a mechanical level? Eric?
Because I have a concern every time it's with
Yeah.
the state, you implement it.
Yeah, and then sure, each person carries around an integer, and each time they get infected, you increment that integer. And that would keep track of, for them, how many times they've been infected, right? Could you put in place rules then that like might, if they've previously been infected, and sought care, could you keep track of the fact that they have sought care previously? Yeah. Could you have that affect their future behavior? So if they've sought care in the past, they're more likely to be willing to do so again in the future? Yeah. Track aspects of history, right? I do want to ask, suppose now we go over to our here. Suppose we want to keep track of how many times people have gotten infected in the population. What do we do that? Okay, Eric's been it's been on a roll. It's just awesome. My hat is off to him. Pius has also answered a great deal. I would like to see if someone who has not yet raised their hand could say. I with due depth of appreciation for Eric and Pius's leadership, and a nod to several others, like Tina and Kehan and Liam, who have also spoken up, and indeed Shifam and Nicola. Is there someone else who has not yet spoken up who would want to comment? Like, could we keep track of how many times people have been infected here? And if so, what would we have to do? Okay. Okay, yes, yes, it is.
Establish a information flow from all of your stock, all of your models. And into like one accumulation.
Oh, okay, so this is a good, let's play that out a little bit. So suppose you had a stock, cumulative effect. And there was a flow into it. Each time someone is affected, you accumulate effect. Would that tell you? Okay, so could you use that in this case to keep track of how many times people have gotten infected? How many times on a per person basis someone has been infected? On a per person basis. Yeah. That's what I was keeping track of for the AVM, right? How many times each person has gotten infected. That's what Eric helped us think through. Nicola.
The kind of issue with that, not to be like a critical moment here,
Yeah.
but just basically like the main issue is if you have that, you don't know per person.
That's right.
And you don't know per person.
That's right.
Like what goes infected. So yes, the number goes up, but it could have been a person got infected twice, right?
That's right.
But you don't know, you can't fix that.
That's right. And in fact, if I could further that, actually, no, did you want to
Is
say?
it just like you can only find an average of how many times, how
Yeah.
many people, but not exactly?
That's right. That's right. I mean, you could take the cumulative infections and divide by the total population size, right? Kind of per capita people, but it doesn't tell you if is it the same people many times, or is it everyone spread evenly. And in fact, if you think about it, I really want you to appreciate it. For your sake as well as mine. No, seriously, I do want you to have an appreciation for this. Like, if we run this model, let's suppose that we run it and at day 100, we have 50 people infected. 50 people are infected in day. And then we run it to day 200. And there's 50 people there too. Can we, in general, say that's the same 50 people? Or it's different 50? No, in general, what this gives is what I'll say is a cross-sectional view. Like, it gives a snapshot at any one time how many people are infected. It doesn't in general, and there are special cases where the model structure is such you might be able to derive it. For example, if it's such that the infection cuts off after a certain time, no one's infected after that or something, you might know, okay, they've got to be the same people. But by and large, what this will give you is, if we think in general, is a snapshot at any one time what the current state of the population is across this, but it won't tell you the history. It won't tell you if it's the same people now that were there before, whether it's a small group circulating again and again, or whether it's different set of people. You're not going to be able to reason about that. Could you reason about it in an ABM? You certainly could. You can keep track by tagging. You can track their history, and you can say, "Oh yeah, this person was infected. They're infected now, and they're infected. The same person was infected 50 times ago." You might even be able. I mean, you could even keep track. They've been infected since that time, or they were infected. That was 3 times ago in their infection status. You can keep track of all that. Here, in general, you cannot. What you have is a count of anonymous people, a count of faceless, nameless, sort of formless people that you're not sure who they were, but there's a group of them that was there now, a group there later. And for a particular model structure, you can actually, you can keep track of how many have left here and gone around, and you could try to keep track of something like that. But in general, for a larger model structure, you're not going to be able to do the accounting to even found really well how many of those people were the people who were infected 100 times. So, yes,
So, I mean, you can have a half a person.
you can have a half a person. You can have a 100th of a person.
That doesn't.
That's right.
Can't.
And this actually makes a difference in some cases. So there was actually quite a prominent, one of Canada's most prominent modelers wrote a paper on drug-resistant gonorrhea, and showed that certain policies they seem to make sense from the standpoint of treating people faster and treating people with more context. But what he showed is that actually with a model like this, they led to even worse comebacks of drug resistance after that. So it was like you were torn because you wanted to do the best job treating people, but if you do that, you will end up having worse drug resistance problems. It seemed like a real quandary. And what we showed actually, we created an agent-based model that had basically the same equations, but it had no possibility of fractional people being infected. If it got down to 1, that was very different from 0. If it went to 0, it died. And what we showed, same assumptions and so on, but not allowing fractional people, not allowing 100th of a person to be infected, 1,000, totally different policy implications. It eliminated this problem with drug resistance, and it led to it being much more favorable to treat because it did not blow back. Their model depended on the fact that even if 1,000th of a person, 10,000th of a person was still infected, it could pop back. And that is not going to be possible. Now, there are subtle issues. Well, what about if there's people outside the scope of the model who come in and can bring in, and there's some subtle issues there, but it was a big difference that suggested, real caution in interpreting this result. Anyway, those are my comments for today. And I will look forward to seeing you on Thursday.